the region dt and the region whose area is given by the integral from 2 to x of 3 plus 2t dt. So what you do is you say, all right, here's 2. Here's 5. If you integrated that function from 2 to 5, that's like 3t plus t squared from 5 to 2. So 3t plus t squared from 5 to 2. Evaluate.
She said, I hope your grandma's having a great day today.
So you have 15 plus 25 minus 10. So you get 30. So it says sketch the region whose area is given by that function. So we need to sketch a region that goes from 2 to 5 with an area of 30. So you would make a rectangle. And what would the height of that rectangle have to be if it needs to have an area of 30? 10.
Thank you.
What's yours? Oh!
I'm confused.
It says sketch a region whose area is equal to that integral. We found that the integral was equal to 30. So we sketched a region of a rectangle that would have an area of 30. Now it says show by differentiating that 3t plus t squared is the antiderivative of 3 plus 2t. So if we call f of x 3t plus t squared, the derivative of that is considered lowercase f, or f prime x. Derivative of 3t is 3. Derivative of t squared is 2t. The fundamental theorem of calculus says that if you take the derivative of an antiderivative, so derivative of an antiderivative, it would be equal to that original function with a change of variable. So again, it's like saying, okay, here's the original, here's its derivative. Now I want to integrate that back again from here to here. So if you integrate this from there to there, so it's like integrating from x to 2. You get 3x plus x squared minus, and we already know what 2 is, negative 10. Now it says take the derivative of that. So it's like taking the derivative of 3x plus x squared minus 10, which would become that is the fundamental theorem of calculus. It is weird, it is gross. It essentially says if you take the derivative of an integral evaluated from a number to a variable, it simply becomes that variable plugged in to the function. See it? Now, what would happen if that variable up top wasn't just an x? That's what we're going to investigate. That's where the fundamental theorem gets a little bit more complicated. So right now, we're evaluating from a number essentially to a number because x represents a constant. Derivative of a constant zeroes away. Why? What? No, I was asking why he was making that noise. So if f of x is equal to x cubed plus cosine x, what's the indefinite integral of that function? So what's the indefinite integral of this function? 2 for the 1/4.
Oh, wait, no.
Yeah, you're right.
Yeah.
I said plus C.
Okay.
Didn't I remember?
Mm-hmm. Never forget that.
What's the derivative of that answer?
Well, I didn't write this.
The original.
These FTC is essentially acting kind of like an inverse property, right? What's forward is backwards and backwards is forwards. They kind of cancel each other out and you end up with the original. That's what the fundamental theorem of calculus part 2 says. It is more useful when we start evaluating integrals that are to other functions. So like right now we're looking at like evaluating an integral from a number to a number.
It's just like if we were to say the square root, or the square of the square root, then that's the original.
Kind of, yes, exactly.
That seems to be the
There becomes a use for it down the road, and that's what we're getting to.
square root.
Okay, so here's your definitional stuff, right? This, and now the wording shall match perfectly. It says, let f be a function which is continuous on the interval a to b. Then the function capital F of x equals the integral from a to x. It equals the integral from a to x. So no longer a to b. It's from a to a variable function, not a number. So from a to x of f of t dt. This is what we refer to as an indefinite integral or antiderivative of f. Okay. This is fundamental theorem of calculus part 1. It says the integral from a to b of f of x dx equals f of b minus f of a. That is the application. Let's find the area from point B to point A. Close the door, get a number, we're done. Part 1 will always be a numerical answer. Part 2, not so much. Part 2 is more of what we're looking at now, where it is going to be like a functional answer. No. So part 2 is essentially saying the theorem presents an astonishing connection between differentiation and integration. If f is continuous, then the function's antiderivative has a derivative at every point, and we say that that derivative of every point is lowercase f of x. Since it's such an important part of the course, we prove it.
Oh my god.
So in order to prove it, we go back to the definition of the derivative.
Oh.
Definition of the derivative involves a
Limit.
limit. You know, it's been so long.
I think
You want to nod? Like, I was having a good day.
So let's start our proof the way we know how. Let capital F of x equal a to x of f of t dt.
Stop.
Let's take the derivative.
Okay.
Develop ALS.
By definition, what's the derivative of f prime of x look like using the definition of the derivative? Okay, it's the limit as h approaches 0. What would you put at the top? What's in the numerator?
F of A minus F of A plus H.
close. f of x plus h, where it's capital F, because we're finding capital F prime, minus capital F of x, all over. Yep. So good. So again, that's the definition of the derivative. What do we know is capital F of x plus h in terms? This is f of x, right? So this would replace this. So how would x plus h change? This is f of x, right? So this is going to go in here.
So would you then take the distributive kind of where you have that plus f of x or plus f of h?
Kind of. It would just change the upper bound. Because what's the rule? The rule in functions is if I change this to x plus h, I change all the x's. Well, where are all the x's? The x's are at the top of the bound. So the top of the bound would become x plus h. Yes. I just want to save myself some space. So this is simply like substitution, right? All I did was substitute this in for that, using the idea of what we know. And don't forget, we're finding the limit. Think about what our rule for limits said. The bounds have to match, right? So you have to go from one bound to another bound where these two numbers are supposed to match each other. So if I flip this one, right? Can I make the top A? Negative. What else could I do instead of flipping it to make the top A?
Add x plus, x to a.
Yeah, if I move this over as a positive and I put it over there, so I flip this one. Because then it would go x to x plus h. Somehow that to me is prettier. But do we see what I'm saying?
Yeah.
Like we're going to turn this to a positive. So that would flip my bounds to x and a. And then if I brought that in front, the a would go to a. Like you would just rearrange your terms because it's commutative, because it's addition. So we get the limit as h approaches 0 of the integral from x to a of f of t dt plus the integral from a to x plus h of f of t dt all over h. So now these bounds match. So I get one nice pretty integral. What does that kind of look like? What does this look like? What if I rewrote it for you like this? Oh, somebody just said it, yeah. This represents the average value of the function. 1 over h, because it's b minus a at bx plus h minus x, so you get h. How did we use the average value of the function today? What did we use it with? What theorem do we really love and we never want to use? IVT. Oh, yeah. So, mean value theorem.
IVT.
says that the average value
Immediate mean.
has to equal some value f of c. So what we can do is say, by the mean value theorem
We don't have room.
for integrals, there is at least one point c in that closed interval x to x plus h, such that f of c equals the average value. So what do you think we're going to do with that idea that we're pulling an MVT here? We're going to replace the average value with f of c. I'm sorry. Yes. This is it. There's only one little one after that. Is there another example on your front page? I'm just printing all this.
It's fine. We don't like trees anymore. See, if you have too much oxygen and if the atmosphere was pure oxygen, we'd all die. So it's actually a good thing that we kill trees. Because they're our enemy. They're trying to make too much oxygen.
All sounds survival of the fittest, man, so we're even better.
Okay.
Oxygen is just a one, not a need.
Do you really need life?
I really need a puree sandwich. I really need
I
a
get for
Jimmy John.
Okay, your
Actually,
homework's
I've
going
never
to
had
go
one.
back
So,
into the
Jimmy
book.
John.
A Jimmy John. Never had
Or,
Really don't.
yeah, or a firehouse.
At the end of the day,
I had a
really
firehouse.
don't.
Firehouse.
Or a Jersey Mike.
Firehouse in New Jersey. Can we go back to? I could kill some.
I like Firehouse
better
than Jimmy John's.
I want to go.
I like
Yeah.
I like Firehouse for a hot.
Tracker.
Yes. Okay.
I don't
I
like
could
Jimmy
go with
John's.
that. A Jimmy John's
Yeah,
doesn't
I'm
get
like,
a lot.
Not gonna lie, I like Subway better than Jimmy John's.
Me too.